Hey everyone, Jerry from LlamaIndex here, and in this video I'll talk about an introduction to query pipelines. So just to set the stage, advanced RAG can have a lot of different components inside of it, and there's a lot of stuff that you can do beyond the simple top K RAG over a vector database. So when you're actually building these advanced components, they can oftentimes be deeply custom. Some examples shown here include query rewriting, for instance, transforming the query into another query before you feed it into your downstream retrieval system. Routing, so taking a query, translating it into a set of choices. Retrieval, being able to actually query your vector database and doing dense search, sparse search, hybrid search, etc. Re-ranking, taking in all these different nodes and actually reordering them based on the query using a more fancy model than dense embedding search. Response synthesis, actually feeding these contexts to the LLM to synthesize a response. And of course, a lot of other components, right? You can include arbitrarily complicated prompt chains, tool use, other modules like other storage systems, graph stores, vector DBs, SQL DBs, and etc. And so this diagram from excellent blog post here showcases just a snippet of the different components of advanced RAG. So our goal in this video is to really introduce some abstractions that help you, one, abstract away some common patterns in composing some of these advanced RAG workflows. Two, letting you easily define custom workflows. Three, reducing boilerplate code and being able to actually string together different components. And four, improving some systems efficiency, being able to get stuff like streaming and async out of the box. So today I'll be talking about query pipelines. Query pipelines are a declarative query API that allow you to chain different modules into a DAG or directed acyclic graph. In future videos, we'll show how you can even compose or combine this into an agent so you can actually do loops over this DAG and therefore create a more sophisticated system. But for the purposes of this video, we'll do an introduction to how this syntax and this overall API allows you to compose these advanced RAG workflows. In the diagram shown here, it shows you a basic RAG workflow with re-ranking and query rewriting. And so given a query, you might pass it to a prompt, which you then pass to an LLM to then rewrite the query. And of course, from there, you send it through the retriever, re-ranker, response synthesis. And of course, for these three modules, at each stage, you also want to pass in the generated query string as well. So in the end, you have a DAG. And when you execute this entire DAG, you get back a response. You can also represent this as a set of nodes and edges as shown in this diagram right here. Some of the features of this query pipeline include being able to concisely express simple chains. So for instance, feeding in an input into a prompt, then an LLM, then an output parser. This is a pretty popular workflow these days, and we let you do it in a very concise but also very readable manner. We also let you express an arbitrarily complex DAG, similar to the example below or beforehand, but actually even more complex. And we'll walk through a few interactive examples on how this works. And so we will show you, for instance, how to compose RAG systems, tool use, and all that stuff in this video and also subsequent videos. In this screenshot, you can see basically two modes of using the query pipeline. And again, we'll go through the notebook walkthrough. But in the first stage, you can see like a sequential chain where, given a query pipeline, you can instantiate what we call like a linear chain, right? And this is just a sequence of values and every subsequent module follows the previous module. And so an example of such a very simple chain is just you chain together a prompt and LLM. And when you pass an input, it flows through both modules and gives you back an output. A more complex, DAG might require our DAG syntax. And here we just show you a very basic example where you can define stuff kind of more like a graph. You define the set of nodes where you add the modules. In this case, it's also just a prompt and LLM. It's a very simple example. And then you can also define the link between these modules, between the prompt and also the LLM. And, regardless of how you define this, you can combine these as well. You run this pipeline and you get back the response. You feed in the input that the first component expects, like the root module, and then you get back the output of the leaf module. You might ask, before we jump into the example, why do we want to do this? And it's a good question, right? because you can actually orchestrate all these workflows without the query pipeline abstraction by just imperatively using LlamaIndex modules. We have all the modules for LLMs, prompts, retrievers, response synthesis. You can just write the Python code, in a function with if statements, while loops, etc., to basically achieve the result that you want. It's fine either way, I think, but we thought a little bit about this, and there are some potential advantages of using a query pipeline. Some of these include being able to express common workflows with fewer lines of code or boilerplate. For instance, if you're stringing together like a prompt, LLM, output parser, it's readable to just define it as a query pipeline. You can do it in one line of code, and you don't have to worry about like string conversions and those types of things. There's a certain element of just like readability when you can actually compose things into a chain or a DAG. And we also will show you how to actually visualize this. So it's kind of nice to just show what the pipeline looks like through NetworkX. Additional benefit is just from a system side, you can pass callbacks everywhere under the hood, so that tracing is baked in. We have a variety of different partners where we enable tracing. And in this example, we'll show you an example with Rise Phoenix. And then in the future, there's also some other benefits. By having a more declarative syntax, you can have potentially easier serializability of these components, which makes it a little bit easy to, for instance, like deploy this to a different server or port this to someone else's machine. But that's kind of something that's more work in progress. So in this video, we'll go through an introductory guide to using the query pipelines. We'll go through basically these two docs in the documentation. If you click on these, you can find these in the docs yourselves. One is an introduction to LlamaIndex query pipelines, and another is query pipelines with async and parallel execution. And so we'll actually just directly jump into a notebook example that covers both of these aspects. So let's go through a walkthrough of how to use LlamaIndex query pipelines in both simple and advanced workflows. So we'll go through some basic stuff of just prompt training, and then expand to more fancy, RAG, retrieval use cases, and then also go through some use cases of async and streaming. So let's get started. The first thing we'll actually do is just set up an observability tool. LlamaIndex provides integrations with a lot of different observability tools with a very easy to use interface. So in about 2 to 4 lines of code, you can set up trace, callback, and by calling set global handler, you're able to log all downstream traces to a provider. In this case, we'll use Rise Phoenix. And let's actually just go through this. And we'll also define some imports. So here, you'll see that there's one main import, which is from LlamaIndex.queryPipeline, import query pipeline. All other imports will be used in downstream modules like LLMs, prompts, vector stores. The next part is we'll load in the classic Polygram essay. This is our favorite example if you follow the quick start tutorial of LlamaIndex. And you'll see that the docs look something like this. What I work on. After we load in the documents, we want to define a vector store over these documents. So we call vector store index.fromDocuments on the docs. This takes in the documents, parses it, transforms it by chunking it into a bunch of little chunks, and then calls an embedding model on each chunk and puts it into an in-memory vector store. Of course, we have a lot of different vector store integrations. We also have a default chunk size and embedding model that we use. And then afterwards, we persist it onto storage. So we call storage context.persist into storage. This is just some wrapper code that says, if it doesn't already exist, build it. If it already exists, then just load the index from disk. So let's call all this. Now we're ready to go through some of the use cases of query pipelines. In the very first example, we'll just chain together a prompt and LLM. So we actually don't use the vector store index right now, but we'll use it in a few subsequent sections. In this case, we'll just do the simple workflow of we have a prompt and an LLM, and let's use our query pipeline syntax to combine them together. If the prompt is please generate related movies to movie name, where movie name is a template variable, we then want to pass the formatted prompt into an LLM. What we can do is define a query pipeline that chains a prompt template and an LLM together. That way, given any sort of LLM, it'll first go through the prompt template, and the output is a fully formatted prompt that then gets passed into the LLM, and then the output is the LLM output. So let's run this very simple example in action, where we do output equals p.run, movie name equals The Departed. You'll see that by calling verbose equals true, it logs the inputs to each module. And then let's take a look at the output. And we'll see a list of 10 generated movies. Just a quick note on this declarative syntax of a query pipeline versus the imperative syntax that you could just do yourself already. You can absolutely create this using an existing LlamaIndex modules. And this actually just walks you through what that looks like. Given a prompt in LLM and given an input, you have a movie name, The Departed. You just need to call prompt template.format movie name equals movie name. Take the output and then pass it in as a chat message to the LLM to use llm.chat. And the chat message is a container that takes in some text as well as the role itself. Once it takes in this input, it generates the output, and we can run this and we'll get back the same result. You'll see that, you can basically do either one. The main advantage of a query pipeline is that the syntax is a little bit more concise, a little bit more readable, and that's just one of these advantages. And you'll see some of the other advantages down the road as well, including ease of visualization and being able to run stuff like async in parallel under the hood. After combining the prompt with the LLM, let's add an additional module of output parsing. So let's say we actually want structured outputs. So what do? If we want an output like this, where we have class movies, where movies takes in a list of movie objects, and both movies and movie is a pydantic model, right? Each movie contains a name as well as a year of the movie, and movies just contains a list of movies. Then we can add this as a pydantic output parser. A pydantic output parser, it just takes in some string and then parses it out, the JSON from that string into a pydantic object. And this will be the last component in our chain. The other component that we're going to need to modify is the prompt, where instead of just saying, please generate related movies, we're going to need to modify a little bit to also tell the LLM to output stuff in JSON format. So here we see this is what the JSON prompt string looks like. Please generate related movies to the movie name. Here is the JSON schema to follow. So this is the output pydantic schema and output a valid JSON object. We can now define the query pipeline chain, which now contains this modified prompt template, the LLM, as well as the output parser. And if we run this on, for instance, Toy Story as a movie, we'll run through all three modules and get back a JSON that goes into the output parser, and we get back a pydantic object. This is a movies object with movie Finding Nemo, Cars, Monsters, and The Incredibles. So that's output parsing. And next let's walk through streaming support. So the query pipelines have LLM streaming support. Streaming is a fundamental part of having a good UX, whether you're building stuff in a notebook or building a full stack application. And you just need to toggle llm.asQueryComponent streaming equals true. Here, if the LLM is the last component in this overall pipeline, then the output of this pipeline will be streaming. And if it's a middle component, then the outputs will be collected and then passed to downstream modules. So let's walk through a basic chain of multiple prompts with streaming, where the first prompt is please generate related movies to the movie name. And then the second prompt is given some sort of text, which is the set of movies, please rewrite this with a summary of each movie. And the output here, you see we define an LLM object equals OpenAI, but then we just call it llm.asQueryComponent streaming equals true. Why do we do this? It's just because the query pipeline expects generally a set of query components. When you pass in a default object like LLMs or query engines or retrievers, it actually gets auto-converted under the hood. But you can, of course, explicitly define this if you want. And when you explicitly define this, you have the option to pass in additional parameters like stream equals true, as well as partials. So this chain contains a prompt, the LLM, as well as the second prompt, an LLM. And if we run this over a given movie, The Dark Knight, it will run through all these different modules, and you can see the output is streaming. Of course, you can also feed the streaming output to an output parsing module as well. So given a basic JSON prompt template, pass it to an LLM that is streaming. You can parse it to an output parsing module, and then you can see the structured output right here. The next step is to show you not just how to do prompt orchestration, but also build an end-to-end RAG pipeline. And in this first example, we'll show you a basic query rewriting and retrieval workflow. And this will cover some basic retrieval concepts, such as query rewriting, as well as hide, and then we'll plug it into a retriever. Here, we can still define a chain where the first prompt is please generate a concise question about Paul Graham's life regarding the following topic. So your first input is a topic, and then this will convert it into a question. And then the second prompt says, please write a passage to answer these questions. Try to include as many key details as possible. Note that this does not actually take in any context. It just tries to use the LLM's priors to answer the question. So this is essentially the hide technique, right? Given a question, try to hallucinate the answer. And then actually use that answer, the hallucinated answer, to as the input to a retriever to try to fetch relevant results. So this query pipeline contains the first prompt, generate question, to LLM. Second prompt, which is the hide prompt, generate passage, to LLM. And then take the output and pass it to a retriever. We can ignore this re-ranking module for now. I'm going to comment this out. Now, given input topic college, we'll run this, and then it'll actually run through all 4 of these modules. Given an input topic, please generate a concise question about his life regarding the following topic. You can see the input is how did Paul Graham's college experience shape his career and entrepreneurial mindset? And then this is the hallucinated answer. This is a good time to actually jump to Phoenix. And you can see that all the traces and chains that we've already called have already been logged. And so from the most basic single LLM calls to the slightly more advanced multi-LLM calls. And so here you can see that the items that we've logged are 2 subsequent LLM calls, question generation, and then passage writing. So this is the hide prompt. And then the retrieval method, right? And the hide passage, given an input, will hallucinate the answer. You can see that it says Paul Graham went to Cornell, which is not true, so that part is hallucinated. But then the idea is that you use this hallucinated passage as an input into the retriever to try to fetch the actual knowledge from the knowledge bank. And these are the set of output documents. So definitely encourage you to check out these observability integrations. They're pretty neat, and it's a nice way to debug your flow. So that was actually just the retrieval flow, but now let's actually create a full RAG pipeline. To create a full RAG pipeline, we need to use a slightly different syntax because we can't just define a chain. A chain just assumes that modules are linear, and so one module follows the previous one. But to define a full RAG pipeline, some nodes might have multiple outputs or multiple edges. Some nodes might take in multiple edges, and so you need a more expressive syntax to actually represent that. Basically, you need a graph-like syntax. So to define a RAG pipeline, you essentially just need to define some sort of graph. This is a very declarative approach towards building a pipeline. And in this first example, we'll show you how to build a RAG pipeline with query rewriting. So this RAG pipeline is just consists of the following components. It takes in an input, rewrites it into a query, passes it to a retriever, then a re-ranker, then a response synthesis module. So the modules here is, again, question generation given a given topic, passes it to the downstream retriever, then a cohere re-rank module, and then tree summarize. This is a response synthesis module that takes in input context or input nodes and hierarchically summarizes it given a query to try to answer a question. So this is a core module in LlamaIndex. So let's run this. And then once we have these modules defined, the next step is to define the query pipeline. You see that here, instead of defining a chain, we first actually just register the modules. Each module contains a key mapped to the module value itself. So here's query pipeline, here's LLMs, prompts, retrievers, summarizers, re-rankers. So let's run that. The next step is to draw links between these modules. And instead of, again, kind of like defining a chain, we'll just manually define the edges between these modules. We'll link the prompt to the LLM, similar to before, and then the LLM to the retriever, right? So inputs flow through the prompt to the LLM, gets rewritten into a query. That query goes into the retriever. This retriever, the output of this retriever, goes into the re-ranker. But the main thing is the re-ranker actually takes in two inputs, right? It takes in the nodes from the retriever, but it also takes in the original input query. So actually, when you're defining these links to the re-ranker, you need to explicitly specify which input is corresponding to. And this is what you do through the destination keys. So the des key nodes is the re-ranker expects nodes, and this is what the retriever supplies. The re-ranker also expects query strings, and that's what the LLM supplies. So let's run that. You can take a look at the summarizer required input keys, which is, again, query string and nodes. Next, we can actually visualize this overall graph. And this is a nice property of a query pipeline, which is because it's declarative and you define this as an overall DAG, you can easily visualize this. Here's an input prompt to an LLM, and then the LLM goes to a retriever. This retriever goes to a re-ranker along with the input from the LLM, and then the summarizer takes in the outputs of the re-ranker as well as the LLM. Let's run this. You'll see we've run all the modules end to end, and we get back a final response. Great. The next step is to show you what a RAG pipeline looks like without query rewriting, which is and sounds very similar. And actually, the main reason we show you this is the use of a special component called the input component. So in this case, we do from LlamaIndex.query pipeline import input component. And the main use for the input component is in cases where you actually want to link the input to multiple downstream modules instead of just one downstream module. In that case, you actually need basically a special placeholder component that allows you to register the input as a module. So here we register it under input as a key to find the input component. And then we add a link from the input to multiple downstream modules. To set up a RAG pipeline, the input, which is the query, needs to be linked to the retriever, but also the downstream response synthesis module, right? Like both of these take in the input, and this essentially provides you a placeholder variable to do this. So we'll run this, and then run this RAG pipeline. What did the author do in YC? And this is the classic RAG pipeline, without query rewriting or even re-ranking, and then you get back an output. The next section here is learning how to define a custom component in a query pipeline. There's actually a variety of ways to do this. You can, here we show you how to subclass custom query components. And so you define a subclass and implement a set of required functions. And so this is the most comprehensive way of doing so and allows you to import or define stuff like validation, input keys, and so on and so forth. There's also a simpler syntax where you can actually just pass in an arbitrary function into a function component. I'll show you a little bit of that. It's not defined in this notebook, but will be defined in subsequent notebooks. Here, to subclass a custom query component, you have we want a subclass to define a related movie component. The main methods you need to implement are validate component inputs, input keys, output keys, and run component. Run component is where you define the core logic. Input keys is where you define the expected input variables. You also can call validate component inputs to decide whether or not the inputs passed in from other modules are valid. So you can throw an error if they're not. And it's implemented similar to a Pydantic validator. So the input just gets passed through and you can modify it along the way. You also define a set of output keys to define the number and the type of outputs that you have. So after you define that, you can define run component. And in this case, we just use the simple query pipeline that we define in the very first section, which again is just a prompt in LLM. Given an input, movie name, just run it through a chain of prompt in LLM to give you back an output. You see we pass in the input key, which is in KWARG's movie. We run this pipeline and then we turn this as a dictionary. The dictionary contains the output keys, which is just output, and then the output value. So let's run this. And then actually, right below this, I show you a very dumb, simple example of what a function component looks like, which also is a way of defining custom components, but is way simpler. All you have to do is import function component, define any sort of function you want, right? This is a dummy foo function, and then just define a function component over it. What this will do is it'll auto inspect the function signature and define those as input keys. It'll inspect the output signature, and then it'll just run your function as a component. So we'll show this more in later videos and tutorials as we set up more advanced stuff, but just keep this in mind for the future. So let's try this custom component out. We'll run this custom component, which again generates related movies, and then also just run it through a prompt afterwards that says, can you rewrite this in the voice of Shakespeare? Right, so at this point, we all know the drill. We take in a component, run it, generates related movies, passes into this prompt, and then an LLM. And this is back to our favorite chain syntax. And then once we define this module and then run this overall pipeline, we're able to get back a list of movies whose summaries are actually written in a Shakespearean voice. So let's finish running, and we can see this is what the output looks like. The output's a list of movies, and this is the output. Okay, last but not least, we'll show you how to do async and parallel execution with our query pipelines. One of the benefits of query pipelines is the fact that you can run them in an async or parallel fashion, and we'll handle the coordination under the hood without you having to worry about whether or not your function is truly async or parallel. So we try to run it in the most optimal manner. This improves latency and takes advantage of your system. So to really take advantage of this feature, we want to define an ensemble retrieval example where we actually take in an input and send it in parallel to 4 different RAG engines, take the results, and then combine them into one response. And so we'll send this, we'll define this toy example, which is similar to ensemble retrieval or some sort of fusion, and we'll define a different query engine over the same data, one per chunk size. So if our chunk sizes are 128, 256, 512, and 1024, we'll define 4 separate RAG pipelines over these chunk sizes, and then send an input to all 4 of these in parallel, and then combine the results at the end. This code snippet just takes each chunk size and splits up the document as such and defines it as a separate vector store, and then stores everything in a query engine dictionary. So the query engine dictionary is just a mapping from the chunk size string to the output query engine, right? So you'll have 4 elements after running this cell. So the key, again, is keyed by chunk size, and then the output is a query engine. Next, we'll construct a query pipeline. you'll see that the set of modules we define include the query engines that we defined above. So the IDs are the chunk size, and then the value is the corresponding query engine. We'll define an input component, a summarizer component, and then what we call a join component. You'll see this in the graph visualization in just a bit, but the join component takes in an arbitrary set of input edges from other modules, from upstream modules. And then similar to the pack syntax in Python, where you can take in some arbitrary components via *args and then packs it into a list, this does something similar. So it takes in an arbitrary number of edges and packs it into a list of objects. And then this list of objects is a single output that you can then pass to other downstream modules. What happens here is first we will add a link from the input to every chunk size. And again, every chunk size is the query engine, right? So we pass the input to the 4 query engines. We then take the outputs of these query engines and link them to the join module. So this join module is taking the outputs from all the query engines. It'll pack them into a list. So now you have a list of different nodes. There's actually a convert function, which will convert the outputs into a node with score. Right, so this is element-wise, and convert it into a list of nodes. And it'll pass this list of nodes to the summarizer, right, with the destination key nodes. The summarizer, of course, also takes in the input query. So let's run this. And let's visualize this. Right. Just to make this crystal clear, we take a look at this input. Here is the input. It links to chunk sizes 128, 256, 512, 1024. These are all separate query engines. All of these outputs flow into the join module, which packs it into a list. This list goes into the summarizer, which takes in the set of nodes as well as the input, and then returns an output. So now that we visualize this, let's run this. We'll see that by running this in an async fashion, await p.arun, it actually runs very quickly. If you can tell, this actually ran all 4 of these retrievers in parallel, the 128, 256, 512, and 1024. All these query engines were run in parallel, and the final output is 3.53 seconds. Right? And the benefit of running all these in parallel is each of these actually requires an LLM call, so it's not just retrieval. So it does legitimately take some time. In the meantime, if you compare this with the synchronous method, you'll see that it does run everything sequentially, right? 128, 256, 512 doesn't take advantage of parallelizable function calling. And then at the end of the day, it takes 8.4 seconds. So that's all the sections in this introductory query pipeline video. And of course, we'll highlight more advanced use cases and other components and exciting features in subsequent videos. But thank you for listening, and take care.